Thank you for giving the opportunity. First of all, I want to thank Professor for bringing me here, and I want to also thank Professor Homsen for giving me a paper that was crucial for developing the whole talk. Okay, so the title of the talk is On the Off-Diagonal Erdős-Szekeres Convex Polygon Problem. So the problem that I worked on is a variant of Erdős-Szekeres convex polygon problem. So I guess it will make sense first by introducing what the original ES problem is. So let me start off by giving you an example. Assume that we have 3 points on the plane, not on a common line. So 3 points on a common line is kind of a singular thing, right? So by this condition, we say that the points are in general position. So let's say that we have 3 points in general position, like this. Then what do we get here? We have a triangle, right? And that's quite obvious. Now, let's assume that we have 5 points on the plane in general position. By general position, no 3 on a common line, like this. Can you find 4 points among them that forms a convex quadrilateral, convex fourgon? This one, and this one, and this one, right? This one, and this one doesn't work. But we have this, and this. So for example, we can find this fourgon. Can you find one here? This one, right? So the happy ending problem is a theorem. It states that any set of 5 points in general position contains at least one convex fourgon. And as mathematicians, we would like to generalize this further. And that's what Erdős and Szekeres, the godfathers of combinatorics, did in 1935. They have proved that for any finite n, there is a finite maximum number of points you can put on the plane so that they are in general position and they have no endpoints in convex position. So this is very important because they have proved that there is actually a finite maximum number. So if you have at least one more than the finite number gon of n, then you are always forced to get an n-gon. So that's how the general Ramsey type statement works. So we know the exact values of gon for n for small n, like we do for Ramsey numbers. So for example, gon of 3 is equal to 2, gon of 4 is equal to 4. That's what we have seen in previous slides. The fact that gon of n is 5 is equal to 8 is hard, but we have a human proof readable by a human being. And we have gon of 6 equal to 16. Unfortunately, we are not capable of understanding the proof. Szekeres and Peters found this by an extensive computer search. And we don't know the values extending to this list. But Erdős and Szekeres in 1960 conjectured that they are powers of 2s. So this problem is notorious for being very simple, but also being extremely hard. So people consider this as the conjecture of geometric Ramsey theory.
Is it obvious that this is a lower bound?
Oh, so I will mention that at least we can get this lower bound. So there is a construction. Thank you for mentioning that. So people have worked on the upper bounds for gon of n. The very first bound, which is 2n minus 4 combination n minus 2, have been found by the original problem setters, Erdős and Szekeres, in 1935. It is of magnitude 0 to the power of n divided by square root of n. Then, after about 60 years, we have the drastic improvement by 1. of Chung and Graham in 1996. Then we have, how do I say? We have a couple of results following this. A linear improvement, a factor of improvement, 1/2. Then another 1. And another very strange fraction. Then another fraction. Till 2015, but it is still of the same magnitude, asymptotic magnitude. And then suddenly Professor Andrew Sook came up with this drastical improvement of the upper bound. So you can see that if we look at only the exponent, the upper bound is very close to the lower bound, right? Only this small factor is ignorable with respect to n if you take the ratio. So people consider Sook to be the first guy to settle the Erdős-Szekeres conjecture in asymptotic sense. And then there comes Professor Holmson, who I really admire, and Mojorat, Park, and Taros, and they have improved the error term by square root of n log n. So this is currently the best known value for this problem. What I focused on is a variant of this conjecture, the conjecture of Erdős, Tuzel, and Waltra. Our main topic is this conjecture. So before I introduce you this conjecture, let me give you a couple of notations. So I want to introduce what a cap, cup, and gon is. A cap is a set of points in the increasing order of x, so that if we connect two adjacent points in the increasing order of x, you always get decreasing slopes, like this. So, for example, this is a cup 2. This is a cup 2. Oh, cap, sorry. Yep. So this confuses a couple of people, so let me mention that. And likewise, we have a 5 cup here. We have increasing slopes. And for gon, I mean the convex position itself. And we mentioned the number of points involved by saying that this is a 4 cap, this is a 5 cup, this is 6 gon. Now, let's say that we have n, a, and b following a bunch of linear inequalities. We want to define a generalization of this original Erdős-Szekeres problem. Let CC gon of a and b and a, b, n be the maximum number of points in general position not containing any a cap, b cup, nor n gon. Then we can already see that this CC gon function is a generalization of the original Erdős-Szekeres convex polygon problem. We have CC gon of n and n equal to GON of n. Then the conjecture of Erdős, Tuzel, and Waltra in 1996 suspects that the exact value of CC gon is a summation of binomials. It may look a bit complicated, but it is actually a partial summation of Pascal's triangle. So if we add everything in a row, we get a power of 2. So this already claims the original Erdős-Szekeres conjecture. So it seems to be much more powerful, but what Erdős, Tuzel, and Waltra have shown is that this conjecture is actually equivalent to Erdős-Szekeres conjecture. So I'm going to tell you why this is true. However, unlike the original Erdős-Szekeres conjecture, this variant has not been investigated that much in literature, except for the original paper by Erdős, Tuzel, and Waltra, and the one by Balko and Waltra that I will mention. So that's up to my best knowledge. If you found any other works involving this variant of conjecture, please let me know. I'll be happy to hear about it. So our result is this. First, I thought it was the theorem, but Professor, I'm sorry for this. I just realized yesterday that the proof for this conjecture was wrong. I want to propose the following conjecture that CC-gon of A and N has this asymptotic upper bound. We have a tight upper bound like we have found for the general Erdős-Szekeres problem that has been found by Suk. Then, this is our main result. We improve the previously known bound of CC-gon of 4 and N by this value up to a square root factor of N. Okay, so this is our result. If you have any questions, please feel free to ask.
Was it like this in your previous talk?
No. In previous talk, this was a theorem.
Right? Yeah, and also the second one.
Yeah. So this remains a theorem, but this...
No, I was thinking, in my handwriting was n choose 2 minus 1 over 64 scale with it. Maybe I made a mistake. Anyway.
Okay, I'm not sure, but yeah.
Yeah, I did that. Anyway. Right.
Okay, anyway. So, from now on, I'm going to first introduce you why have I posed this conjecture, and why am I interested in like this CC-gon of 4 and N value. And to introduce you this one, I first have to introduce you the argument of Erdős-Tusa and Waltra. So we first started with the very classical problem of Erdős and Szekeres called the Kapka problem. So what we have defined is CC-gon. We want no cap, no cup, no gon. Instead of that, we just want to force no cap and no cup in this Kapka problem. Erdős and Szekeres have already settled this problem by showing that CC of A and B is equal to this value. And let me note that CC-gon of AB, A plus B minus 2 is exactly this value. So they have proved a kind of diagonal part of the CC-gon values. This gives us the bound of G1 of N by CC and N, which is the original bound they get. And the proof is recursive. If any of A or B is 2, we should have the maximum point 1. And this equality works. So I'm going to show you a quick proof of this equality. First, we want to show that CC of AB is at least this one plus this one. So let's say that A and B are larger than 2. Then we have this magnitude of sets, a set L. Oh, sorry. This one goes for L, and this one goes for R. Sorry about that. So we have a cap B minus 1 cup free set L and A minus cap B cup free set R by our recursive construction. And we want to construct a cap B cup free set S, which is of the magnitude of the size of L plus the size of R. Then what we do is here with this one. So let's say that R, L, and R sort of look like this. Then what we do is to first squeeze L and R vertically like this, so that any point in L, any 2 points in L, or any 2 points in R have very small slope in magnitude. We squeeze them very tight, very, very tight. Then we align them like this, so that horizontally L comes first, vertically R goes on top, so that any segment connecting L and R have slope much larger than the ones connecting 2 points in L and 2 points in R. Then can you see why this is an A cap B cup free set? Like we can't find one A cap here. If we want to exploit the point here, then we can use at most one point from here. if we have 2 points here, then we should use this one, then everything drops. So we cannot use more than 1 point. So it's either a minus 1 cup, this, or a cup here. So this construction gives us a cap B cup free set, and this shows the lower bound part. Now let me prove the upper bound part. For the upper bound, we have the following decomposition theorem. They haven't explicitly mentioned it, but this is essentially the argument of Erdős-Szekeres. Any A cap B cup free set is a disjoint union of an A cap B minus 1 cup free set and A minus 1 cap B cup free set R. So we can kind of reverse the construction process. So let me give you a quick proof. I'm going to use the board if it's necessary. So let L be the set of starting points of all A minus 1 caps in S. So like let's say that this is S. Every time we have an A minus 1 cap, which is the tight cap, we add this point to L. Right? So, and we do that for every possible A minus 1 cap. And let RB is complement. First, I want to show that L is A cap B minus 1 cup free. R is A minus 1 cap B cup free. So first I have to show this one and this one essentially. If R contains an A minus 1 cap, so we exclude all the starting points of A minus 1 cap, and we define them to be L. Then if R contains an A minus 1 cup, then this very starting point of this cap should be in L2. So we get contradiction. So R is A minus 1 cap free. And if L contains a B minus 1 cup, like this, so this is a B minus 1 cup consisting of all points in L, then this endpoint should be the starting point of another A minus 1 cap, right? So this implies either the existence of A cap or B cup. The reason is because let's say that we have this cup and this cap, all right? If we look at the angles of segments with endpoint, this one, if this is a cap, we can extend this cap to this cap. We get one more. If it's like this, we can extend this one to this one. So this shows the decomposition theorem, and we get the upper bound too. So we can see that for this cap-cup problem, everything is recursive. Any tight set can be divided to smaller tight sets. And the one that you mentioned, the lower bound, is here. Using this cap-cup construction, we can find 2 to the power n minus 2 points avoiding n gone, like this. We do the same thing with points avoiding n cup and 2 cap, n cap and 2 cup, and we stack them like this. And Erdős-Szekeres conjecture states that this set is tight. What's interesting about this construction is that if we take only the subsequence of this whole construction, we already get A cup, B cap, and gone free set. So this already proves the lower bound of conjectured value of CC gone. Moreover, we can replace the subsequence with the tightest possible A cup, B cap, and gone free set. We get another n-gon free set. So if we could improve this subsequence by more points, that is, if we found any counterexample of ETV conjecture, then we find a counterexample of Erdős-Szekeres conjecture. Have everybody got that? So this is how they prove that their stronger conjecture is actually equivalent to the original one. So you can see that the conjecture of Erdős-Szekeres and Valtra essentially states that if we have this particular tight, conjecture to be tight, construction of points for Erdős-Szekeres problem, ETV states that this sub-configuration is tight in a sense. So as the sub-configuration becomes larger, we have the layers of conjectures in the increasing order. The whole thing is the hardest one. You take n-1 subsequence. This is unknown, this is unknown, this is unknown, up to CC 4 NN. This is even unknown. And then we have the classical Kapka problem where we know the answer. And this is the reason why I want to focus on this value of CC 4 NN. If we can find a counterexample for this one, we find a counterexample for the Erdős-Szekeres conjecture. If we could prove that this is true, this will be an evidence of this will be kind of indirect evidence for how the Erdős-Szekeres conjecture will be true. So we have found the exact value of CC of A and B that was done by Erdős-Szekeres, and we know that Andrew Sook have completely settled the GON of n by asymptotical bound. We want to see if CC gon of A, B, and n can be approximated by an upper bound. So obviously we have the easy upper bound of CC and GON, but they are far from conjecture lower bound. And I want to propose the following conjecture. So the conjecture states that for CC gon of A and n, the upper bound is 2 to the power small o of n, which is asymptotically small in the exponential sense with this binomial term. This bound will be asymptotically better than the obvious bounds. And also, I made this bound so that the upper bound is tight by a factor of 2 to the power small o of n. So I strongly believe that this is true, but and to be honest, I thought I could find a proof for this upper bound, but yesterday I went over my proof and realized that I was wrong. So I changed this slide today. Sorry about this. But still, if you are interested in this problem, I guess it will be very great to work on this problem together. I think it is very meaningful. Because in a sense, this upper bound states that this subconfiguration is asymptotically tight in a narrow sense. So this is much finer upper bound than the original Andrew Sook's argument. So, well, this is not the true. This is not true. Ignore this. Possible proof. So what Andrew Sook did was to use this grouping lemma. So what Andrew Sook did was to take a large point set P. Then we can prove that if P is large enough, then we can find either a K cup or K cap, so that the triangles we can make above the cup or below cup contains a positive fraction of the whole thing. So like if you have a lot of points over here, then we can find n to the power of 2 over 3 points among here, so that with the triangles we make from this cup, there is a positive fraction of the whole point, which is alive in this triangle. So we have already seen that the tight construction like this, right? So we want to kind of like mimic this configuration by trapping everything in this small triangle. And the argument of Suk goes by either finding a very large cup here, very small caps, which can be connected to form a very large n-gon, or like left cup and right cup that can be combined to form a n-gon. If you're interested, I'm going to give you a reference and maybe we can talk about it. What we could find is this following CC-gon, following improved upper bound of CC-gon 4nn. So this conjecture, CC-gon of 4nn is equal to, so I was wrong. So I guess this is the, this we have an error. It should be plus, I guess. Sorry about that. This is the easiest unknown case of the hierarchy of conjectures. And we have the easy bound, low bound for the construction, and the upper bound for the CC problem. And Balko and Vulture have found that we can improve the upper bound by number 1. And they have found that the value is equal, the conjecture is right for n less than or equal to 8. And we have proved the following. Instead of the original upper bound, we could improve the upper bound by a factor square root of n. So, the idea for the problem, the idea for this theorem is as following. So, before that, I want to mention that actually finding this value is much more sensitive than the conjecture that I posed in the previous slide. The conjecture that I posed in previous slide is tied up to the factor of 2 to the power small O of n, but this one, everything is polynomial. So everything is very small in a sense. And we want to get it as close as possible between two small polynomials. So the idea is as the following. We call a segment type 1 if there is a 3 cap ending with a segment. So I plan on to finishing this earlier and give answers to your questions, and maybe if time remains, I will go over the full proof. But this is the sketch. So let's say that we have a set S with no 4 cap nor n-gon. Then let's call a segment connecting 2 points in S of type 1 if there is a 3 cap ending with this segment. And let's say this segment of type 2 because there is a 3 cap starting with this segment. Okay, so for example, if we have this particular configuration, this is of type 2, this is of type 1. And you can see that this definition does not contradict each other. Like if we have a segment of type both 1 and 2, then we get a cup here and cup there so that we have a 4 cap already. So everything is either type 1 or type 2, and we assign any of type 1 or 2 if there is no such like cap. Then we define the functions as the following. We define alpha of P to be the maximum length of a cup that ends in P with a segment of type 1. So this is the alpha P. And beta P is this. This is the maximum length of a cup that starts with P with the segment of type 2.
So what do you mean by segment?
Segment.
Yeah. Is it like any pair defines a segment?
Yes, any pair. Any pair, any 2 different points in S. So this alpha and beta are important in our proof. Actually, I think so. This reveals us the hidden structure of tight four-cap angon sets. So they have many useful properties. So for example, for any P and Q different, the values of either alpha and beta should be different. I'm going to draw you a picture. So let's say that we have P and Q and the segment connecting 2 points.
Can you go back one slide?
Oh, sure.
Just to remind. Yeah.
Oh, no. Okay.
Oh, maximum length.
Yeah, maximum length.
Another one start. These are
Okay, so I hope this cheat diagram makes sense. For any three cup, this one is type 2, this one is type 1. Alpha P is the maximum length of a cup that ends in P with the ending segment 1. Beta P, starting with P, with starting segment of type 2. Then we can prove that this holds. Let me tell you why. First, I have to give you a proposition. If we have any cup and any segment of type 1 that starts with this point. So if we have any cup and if we have any segment of type 1 connecting the starting point of the original cup and another point with lesser x, then this forms a larger cup. And another one is that we can extend to the right by 2. So if we have any segment connected by type 1, then type 2, this is a cup. So in general, if you have two segments with type T1 and T2 which satisfying the following inequality, we have a 3 cup. Okay, so let me first mention this. Then we can, I don't want to delete the cheat sheet. If P and Q are connected by type 1, then we can always extend this. No, sorry. We can always extend this cup of length alpha P ending with type 1. Then we can extend this type 1 segment with another type 1 segment by this proposition. So in this case, where P and Q are connected by a segment of type 1, we have alpha P greater than less than alpha Q, right? And the same thing goes for P and Q connected by a segment of type 2. For this one, beta P is greater than beta of Q. So this in particular proves this theorem. And also, if we have a point P, the cup of length alpha P and the cup of length beta P can be connected to form a large cup. So alpha P plus beta P should be less than or equal to n. So with this map, P from S to this set T is injective. So the magnitude of, so the size of T is the original Kappa bound. So if we inject S to this set by, okay, so we use the method of contradiction. So let's say that we have more than n combination 2 minus 1 over 64 square root of n, let's say. Then we have less than 1 over 64 square root of n missing points in T, in the image. And so after that, I'm going to skip the detail, but by using the properties of alpha and beta, we can use this argument, that argument, and such, so that we can force on n-gon in the final diagram. So this shows the general scheme of how I would do. So I'm going to make n minus 1 cup here, n minus 1 cup there. So this, I hope it makes sense, is a n minus 1 cup with the values of alpha and beta in the diagram. Then with this n minus 1 cup, with this n minus 1 cup, if we have any of the cap over there, we get a contradiction, right? So this should be a cup 2. With this n minus 1 cup, this should be a cup 2. With this n minus 1 cup, this should be a cup 2. So, I have to mention that in the diagram that I draw, every segment connecting to horizontal, every horizontal segment in this diagram is of type 1. Every vertical segment connecting 2 points is of type 2. So that if we connect those points and those points, they will be sorted in the increasing order of x, and they will form a cup. So we already get a n minus 1 cup. What we do is to use a argument so that we can find a more contrived n minus 1 cup, so that we can force a 4 cup here, so that instead of following this line only to force only n minus 1 cup, we force a 4 cup here, so that we can follow this line, then we follow a 4 cup, then another cups here, so that we have a cup larger than the size of n. And that's the general idea of the proof. So the future plan is this. First, this I couldn't modify it. I want a proof of the original conjecture I posed for GON of CC-gon of A and N. I hope a proof will work by using a variant of Erdős-Szekeres proof. And I also think that it would be great if it could prove an improved bound by a vector of linear term. Even this I think it will show the overall structure of CC-gon of 4 and N. Okay, so thank you for listening, and I will answer your questions.
Thank you.
Thank you.